All right, welcome to Physics Video 1.1. We're going to be learning today about distance and displacement. I'm going to try to start every one of these videos where on this title screen here you'll see a list of the objectives. And these basically are just telling you sort of what the point of this video is and what things you should be able to do by the end of the video. I don't always read through them, but do make sure that you take a second and read through them yourself and probably jot them down. So that by the time the video is done, you can go back to them and make sure that you can do these things. Also, I guess since this is the first video for you, I want to remind you that you can pause this video and you can rewind the video. So, don't feel like you need to be writing while I'm talking. Listen to what I have to say, then pause it and write stuff down. Rewind it if you have to, and make sure you take advantage of this. This is designed so that we can use time in class, so I can give you guys one-on-one help rather than me, standing at the board giving notes. All right, so here we go. I'm going to start by just giving you the definitions. So you're going to want to take a second and pause the video and copy these two definitions down. Let me run through them real quick, kind of explain to you what the difference between distance and displacement are, and it'll probably be a little bit clearer when we run through an example or two. Okay? So just to read them real quick. Distance. The symbol for distance is lowercase letter d. Okay? And it is a measure of the total length of the path that an object follows in some time interval. Okay? Displacement, the symbol for displacement is, it's actually the Greek letter delta followed by an x. The Greek letter delta is just this triangle. We'll learn a little bit more about why that's the symbol in a day or two. But for now, just know that triangle x means displacement. That is a measure of the displacement and the direction of the straight line from an object's position at one time to its position at another time. Okay? So again, that'll be a little bit clearer as we go through an example. So first of all, let's do this. Let's talk about units for just a moment. All right? Because both distance and displacement measure length, they're going to be measured in similar units. So here in America, we would use standard units, which could be things such as inches, feet, yards, or miles. And then in Europe, Canada, or physics class, we're going to use the metric system, where we might measure displacement or distance in centimeters, meters, or kilometers. Ultimately, once we really get going, we're going to focus on meters. Okay? So, like I said, let's do an example where we actually have a moving object, and we can talk about both the distance and the displacement. So, here's our object. I have an ant on my screen. And the ant is going to crawl from point A over here to point B. All right, so let's suppose he does that. So, again, the distance is the length of the actual path that the ant follows. So if the ant crawls and does this, and follows this big, long, curvy path, then if we somehow took that line and stretched it out into a straight line and measured how long it was, that would be his distance. All right? So the distance is the length of that solid line there. Okay? Now, displacement is a little bit different. Displacement doesn't care how the ant got from A to B. All displacement cares about is where did he start, where did he end, and how far apart are those 2 points. So to measure that, we'd have to draw a straight line. So I'm going to pull up a little tool here so we can get a dotted line, and I'm going to draw a straight line from point A over here to point B. All right? Now, that dotted line that I just drew is what we call displacement. All right? And if I was to measure that, again, using my ruler, that would give me the displacement. All right? Now, because of that, because the displacement is that straight line, it's always going to be, I guess I shouldn't say it's always going to be, it's never going to be longer than your distance. Okay? So, that's a quick example that sort of illustrates the difference. How does that come into play as we do some problem solving? Well, let's notice a couple things. First of all, as I just said a second ago, the distance can't be shorter than the displacement because the displacement is always a straight line, which is by definition the shortest distance. All right? And the only way that the distance and displacement are the same is if the object travels in a straight line. Okay? So that's going to be our jumping off point. First example I'm going to do is where your object travels in a straight line. So let's do that. Because the displacement includes direction, we need to talk briefly about direction. All right. So in math class, you guys usually use two axes, right? You'll have an x-axis and a y-axis. All right. For the purpose of this chapter, we're going to be doing linear motion, which means that all of our motion is going to take place either on the x-axis or on the y-axis. Okay. So along that x-axis, anything moving in this direction is going to be called positive. Anything moving in this direction is going to be called negative. All right. So if you've got, for example, a car that drives east, that's going to be considered a positive direction, whereas west would be negative. Okay. Similarly, forwards, I'm going to abbreviate, forwards would be positive, backwards would be negative. If you had an object that was moving right or left, right is positive, left is negative. Okay, so that's one category of problems where your object is moving along a horizontal line. Secondly, sometimes we'll have objects moving up and down, like maybe a ball that you've thrown straight up into the air, or a car driving on a road that drives north-south, in which case up is positive, or north would be positive, and then down or negative, or down or south would be negative. Okay? Now, because of this convention, what's going to end up happening is, because if you go back to our definition of displacement, one more screen, the displacement includes the direction, right? So because of that direction, occasionally our displacement will be negative. So what that means to us in English is this. If the object moves in a straight line, well, let's do this. Suppose we had a situation where, I don't know, a car drives east 5 miles. Well, in that case, if it's going straight east, then your distance is going to be 5 miles, and your displacement is going to be 5 miles. All right? But what if we'd had our object going west instead? If we had the exact same thing, but it was driving west, then what would that would do is this. Our distance would still be 5 miles, because the path of the line the object follows is still going to be 5 miles long. But our displacement now, because west is in a negative direction, our displacement becomes negative 5 miles. Okay? So, as long as your object is moving in a straight line, your distance and displacement are going to be the same number. The only difference is your displacement might be a negative if you're moving in a negative direction. Okay? So, what's more interesting then is what happens if the object doesn't travel in a straight line. Okay? So, let's walk through this example here. All right? So, it says, suppose Roy jogs 8 miles west, and then he goes 3 miles east. So, what we're going to do is draw this. We're going to pick a starting point, and we're going to say, all right, he goes 8 miles west. So, there's our 8 miles west. And then, now he's here, now he's going to turn around and go 3 miles east. So there's our 3 miles east. So there's his ending point. Okay? So, to measure the distance that he travels, it's just an issue of how far did Roy jog, right? At the end of the day, he's going to be tired because he jogged 8 miles, he jogged another 3 miles. So his distance is simply how far he jogged total, which is 8 miles plus another 3 miles, so 11 miles. Now, the displacement is a little bit trickier. For our displacement, again, all we care about is how far is it from starting point to ending point. So for my displacement, I'm interested in this red line here. Notice I put an arrow at the end of it, indicating that my start was here and my end was here. All right, and so there's a couple of ways you can figure that out. Conceptually, you can just think about it and go, well, this distance is 8 miles, this distance is 3 miles, so the difference must be 5 miles. And because the arrowhead points to the left, points in a negative direction, you've got to make it negative. All right? Now, for some of you, kind of problem solving like that might be a little bit trickier. So I'd prefer you to be able to do it this way. But that said, for some of you, you want a more systematic way of solving it. So another way you can do it is this. When we found our distance, all I did was I added up the two individual distances, right? 8 miles and 3 miles. You can do the same thing with displacement. Okay? I'm going to take my two displacements and add them up. 8 miles plus 3 miles. But there's a difference. One of my displacements is negative. Okay, the 8 miles, because it was moving in a negative direction, is actually negative 8 miles. And so now when we add them up, negative 8 miles plus 3 miles gives us that same negative 5 miles that we got before when we just kind of did it logically. Okay? So, and again, you'll also notice our distance is 11 miles, our displacement's only 5, negative 5. The displacement is, as we said, shorter. Okay? The final example I want to walk you through is occasionally we'll have problems that take place on a number line. Okay? The number line actually measures what's called position. We'll learn about that a little bit more later on. But suppose we had a scenario where, I don't know, let's say that somebody walked from Bob's Triangle store, where he sells triangles, and let's suppose that they walked from the Triangle store to White Castle and then back to Sally's. Okay? So here's our person, and they're going to walk from the Triangle store to White Castle and then back to Sally's house. Okay? So in order to find the distance, again, it's going to be very similar to what we did before. You're going to have to find the two individual distances. So the first part of the trip, which I am going to go over in blue, he traveled from a position of 12 to 3, right? So for that part, that's going to be, what, 9 miles, the difference between 12 and 3. And then for the second part, he went from White Castle back to Sally's, which is another 4 miles, right? From 3 to 7 would be another 4 miles. So that you get a total of 13 miles. Okay, just by adding up the two parts. The displacement's actually even easier. Let me erase my drawing, which has gotten kind of cluttered here. All right, check it out. Look, here's all that happened. Our dude started here at Bob's Triangle store, walked all the way to White Castle, and ended up at Sally's house, right? Remember, displacement doesn't care about the path you followed. All it cares about is where did you start and where did you end. So while my distance was 13 miles, my displacement is just how far it is from starting point to ending point. So you're walking from a position of 12 to a position of 7, which means that you're going to get the difference between 12 and 7 is 5 miles. I don't know why we keep getting 5 here. And because the overall progress was in this direction, we do need to make it negative. Okay? So, in a very quick 10 minutes, that is the difference between distance and displacement. Tomorrow, we will be learning about speed and velocity. Okay, thank you.